Okay. Today we're going to talk about comparison tests. The first comparison test is the direct comparison test. And there's two ways we can use it. Okay. We can show it to either converge or we can show it to either diverge. But we have to have certain stipulations. Okay. So let's first think of a convergent series. The code word is what? So first of all, we have positive sequences. That just kind of always happens. All right. Now, if we have a convergent sequence, and I guess I should say series. I'm sorry. If we have a convergent series and our sequence is fitting under the sequence that we have for the convergent series, what should be true about the lesser sequence? Okay, then that series is also going to converge. So if you have a convergent sequence, you would want it, I'm saying it wrong. You have a converging series and you know a sequence that fits under the one that you already have, then it is also going to converge. Does that make sense? Okay, visually, can you visualize it?
No. I know what you're saying, but I don't know what it looks like.
Converging sequence. Series. Like that, right? So underneath, if one's sitting underneath, it can't go over, right? Because it's always going to be underneath. Okay? Same thing. Let's say we have a series that diverges. And we have a sequence that is bigger than the one that's in the series that diverges. Then it's going to diverge.
What if it's the one that's -1
Then -2, 2.
Well, if it's just always bigger than that, then it could just be.
Okay, then this test wouldn't work for that. Like, because you have to show me, and this is a part of the test, you have to show me the inequality, stating either bigger or smaller. Okay, if you don't show me that, this test does not work. Also, if it is not obvious that it is 100% always greater or 100% always smaller, probably not a good test to use. Like, you need to be able to convince an Algebra 1 student that this is greater than this, or vice versa. Okay?
Are they Algebra 1?
Freshman Algebra 1 students.
Not seventh grade Algebra 1 students?
I said freshman Algebra 1.
Can't we convince the seventh grade Algebra 1 students?
Okay. Grayson, I'm going to go to you because this was your idea. Which P series could we maybe compare this to? Well, like which P series? Like, yes, P greater than 1, but what specifically would P be? Okay. So we're going to compare to the series n equals 1 to infinity of 1 over n cubed, which we know is a convergent p-series. A lot of this is just writing down the information. We're comparing it to the sum of 1 over n cubed, which is a convergent p-series. Now, which way should the inequality face? The alligator should be eating which one? To the right? Okay? We know for a fact that this sequence right here, the denominator is always bigger in this one, which means the fraction is always smaller. Okay? And since we have a convergent series and our current series fits underneath of it, then it also converges by the direct comparison test. I'll even let you write that. Direct comparison test. So a lot of you are going to know that in your head, right? It's a matter of writing it down. Okay? But do you agree with me that it is extremely obvious that 1 over n cubed plus 1 is always smaller than 1 over n cubed?
Yeah.
Okay.
Yeah.
Oh, I can just split this up into 2, right? Maybe I could before. Why? We can't break apart a denominator. Ole, Jose. Instead, what might be an obvious one to compare it to?
Just compare it to 1 over 2.
Okay. Compare to the sum of 1 over 3. Do you want me to put the n with just the 3?
It doesn't matter in the form.
Okay. Which is the same. And what do we know about this? A convergent geometric series. Okay. Is 1 over 3 to the n plus 2 always less than or equal to 1 over 3 to the n? Is that obvious? The denominator over here is always bigger because it's just plus 2. Okay? Okay, then our series of 1 over 3 to the n plus 2 also converges by the direct comparison test. English class?
Yeah, we're getting brainwashed in there. Well, we're not. Others are, though. I'm about to get like a 40 on my paper that I wrote.
I'm adding an example.
Punish all people
At your pods, you and your partner go through this one together. You have 2 minutes.
I started.
Oh, yeah, it's one over
That's not gonna work. It's not always.
Does it have to be always or from minutes? Oh, it's only from minutes, right?
Why did I start at 2?
So
What? Can't do 1. That's where we're at now. So it has to be 2. All right. So pod 2. What would we compare it to? Compare to. And what do we know about 1 over n? Okay, and so we need to show what needs to be true about the sequence in question and the sequence we're comparing it to if the sequence is divergent. That has to be greater. And is that the case?
what if I just memorize all the So
Then you would have to do DCT inside of DCT.
what if I already
Once it's in, I'll need to then
you do like number 1 and then you have to do something?
But if you do DCT of 1, then it's uses.
Okay, so if in number 1 you use DCT and in number 2 you can compare it to number 1 that you've already proved, then that's fine. Okay, now sometimes the inequalities needed to prove greater than or less than for the direct comparison test don't hold 100% of the time, or they're not obvious. Okay? We can really only use the direct comparison test in a limited number of cases. So we have another comparison test, probably one of my top tests for convergence. Okay.
ICT.
LCT. Limit comparison test.
Gross.
Okay. So all we have to do is we take the sequences inside of our sums and we take the limit of the ratio of the two. And as long as your limit is finite and positive, then either they both converge or both diverge. Write it down and we'll work it down. I'm going to tell you right now that this test is the best for rational sequences inside of our sum? Yeah.
So would this LCT and DCT be one test or two tests?
Two separate tests. Two separate tests. DCT is less work, but you still have to write quite a bit. LCT, you have to take a limit. So basically, if you can compare it, so you take your series, you're comparing it to a series you know something about. 1 over n squared is a convergent series. When you take the limit of the ratio and you get a positive finite limit, then the test in the series in question will also converge. Or if you're comparing it to 1 over n, a divergent p-series, and you take the limit of the ratio and get a finite number, then the series in question will also diverge. Okay? So there's no like figuring out if one's bigger or one's smaller. Your work comes in finding a limit. So go ahead and write this one down. Okay. And you want to compare to a series as simple as you can get. Okay. What is a very simple series that we know something about that we can compare this to? 1 over n squared. Basically, take off all the junk. Our highest term in the denominator is n to the second power. So, let's compare to 1 over n squared. I don't even care about the 3. A convergent p-series. Okay. We're going to take the limit as n approaches infinity of our original 1 over 3n squared minus 4n plus 5 divided by what we're comparing it to. Okay, so what we have is n squared over 3n squared minus 4n plus 5. What's that limit? 1/3. And what's true about the number 1/3? It's positive and finite. Therefore, the series of 1 over 3n squared minus 4n plus 5 also converges by the limit comparison test. Okay. Do you see what I mean when 1 over 3n squared minus 4n plus 5 is pretty difficult to compare directly to 1 over n squared? Like that denominator, there's a lot going on in that denominator. There's no way for us to be able to just look at it and say, oh yeah, that's smaller than 1 over n squared. How do you know? Okay. So when it's complicated in the denominator, it's not obvious to be able to make that direct comparison. We can take the limit. And really, you can do the limit with anything that we did with the direct comparison test also. It's just a little bit more work, right?
Technically, you sort of know it already because you're squaring and not
Okay. What's happening? We're specifically choosing a series to where when we take the ratio, we have the same degree, right? We have the same degree, numerator and denominator, and so it's a nice limit. Okay. Okay, write this one down. What's my right hand? Okay.
So we probably left it. Well,
I expect more from you.
I heard enough jokes.
True, Isaac's felt it. So you should know what it feels like.
Now he's sparking out.
Isaac, what are we going to compare this to?
How about we should go,
And why 1 over n? Okay, essentially we have a 4th degree divided by a 5th degree. So if we just look at those degrees, the leading degrees, I suppose, we have 1 over n. Okay, now we know what's going to happen, right, when we take that limit. Okay? Oh, and what do we know about 1 over n? A divergent p-series. It is important to make the classification whether your series that you are comparing to diverges or converges. That way you know what to do in your conclusion. 1 over n.
Never mind.
Yeah?
Yeah.
Sorry, I didn't mean for it to sound that way.
No, I get it.
Okay.
Come on, Isaac. Come on, you're so dumb.
Nobody said that. Nobody said that.
Just no, not me.
So we're going to take the limit of n to the 4th plus 10 over 4 to the n to the 5th minus n cubed plus 7 over 1 over n. Whoa. Okay, don't multiply things out. I would just multiply by n over 1 and just write that. And you know what's going to happen. We have a 5th degree divided by a 5th degree. What's our limit? 1/4, which is positive and finite. Therefore, the sum, blah, 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 also diverges by the limit comparison test. I shouldn't be lazy, I'm so sorry. So far my phone has only mistaken me once.
Siri.
I think that's a record.
Hey Siri.
What my me?
Hey, Siri.
Yes.
Where is that?
Positive finite. I knew I wasn't gonna squish it all in.
Look at that series.
Yes.
Wait for it. Look at that series. That's a really cool series. Hey, it's a series.
See, it's
Say
It's
it's
learning.
just me.
It's learning.
It's learning.
Okay.
Okay.
You can do it too quick. What if you do the British accent?
Okay, look, it's here.
Okay.
That's because I'm already Siri.
Hello, Siri.
Now I don't want to go all the way through this one, but what if you had something like this? Pay attention, focus. Hold on. I think I need more than that.
Is it a 7?
That's a 7. Okay? Since it is a rational expression, it makes a good candidate for a comparison test. Not a direct comparison, it's too complicated. But what could we compare it to? I heard 1 over mumble, mumble, mumble.
Is that end of the 7?
Yes. You're saying 1 over n to the 1/3?
Yes.
Okay, because essentially we have n squared, blah, 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 over n to the 7/3, blah, 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 blah. Reducing that, you would compare to 1 over n to the 1/3, which is a divergent p-series, and when you take the limit, as long as you get a positive finite number, this will also diverge.
No, we're done.
I don't want to go in there.
You don't want to grade your throwback Thursday?
Okay. Same.
You have 10 minutes. Are you all telling me that you want to open your book and work for 10 minutes?
Well, open the book.
I want
Yeah.
The only way
My phone.
I'm not going to pass these back is if you actually work for 10 minutes.
Will we get a completion grade?
What if we don't work 10 minutes? You won't know until we're done with the 10 minutes.
So you're saying that you don't want to grade these, you want me to grade these, even though we have 10 minutes left.
Like